The National Metrology Center is a public decentralized agency of the Secretariat of Economy in Mexico. It is the National Metrology Laboratory, the national reference in the area of measurements. From the smart electric power grid to atomic clocks and advanced nanomaterials, innumerable products and services rely in some way on technology, measurements, and standards provided by Cesium. To learn more about how you can work with us and make use of our products and services, we invite you to visit our website and learn about our current projects. In this opportunity, we will present some details behind the best standard for the measurement of time in Mexico and the applications of this amazing apparatus. First, we will present basic concepts related with how the human being began measuring time and the definition of this unit in the International System of Units. Then, we will describe how the definition of the second is materialized at Cesium, and finally, some important applications are presented. Well, in today's world, the most widely used numeral system is the decimal, base 10, a system that probably originated because it was easier for humans to count using their fingers. The civilizations that first divided the day into smaller parts, however, used different numeral systems, specifically duodecimal, base 12, and sexagesimal, base 60, to count something, heartbeats for example. Thanks to documented evidence of the Egyptians' use of sundials, most historians credit them with being the first civilization to divide the day into smaller parts. The first sundials were simply stakes placed in the ground that indicated time by the length and direction of the resulting shadow. This division reflected Egypt's use of the duodecimal system. The importance of the number 12 is typically attributed either to the fact that it equals the number of lunar cycles in a year or the number of finger joints on each hand, excluding the thumb, making it possible to count to 12 with the thumb. Since origins of civilization 3500 BC until nowadays, the measurement of time has been a common concern. The timekeeping community have been developing better clocks, sundial, mechanical, and atomic, reaching astonishing measurement uncertainties such as that of the Cesium's clock based of cold cesium atoms, with an expected error of only 1 second in about 100 million years, or 10 nanoseconds per year. Is it not amazing? Today, highly accurate timekeeping instruments set the beat for most of our electronic devices. Nearly all computers, for example, contain a quartz crystal clock to regulate their operation. Moreover, not only do time signals beamed down from Global Navigation Satellite Systems, GNSS, calibrate the functions of precision navigation equipment, they do as well for cellular telephones, instant stock trading systems, and nationwide power distribution grids. So integral have these items-based technologies become to our day-to-day lives that we recognize our dependency on them only when they fail to work. The natural measure of time of society is the day defined by the rotation of the Earth. Due to the elliptical shape of the Earth's orbit, the duration of the true solar day is not at all constant. With the aid of clocks, a day is further divided into 24 hours of 60 minutes, each minute being in turn divided into 60 seconds. The definition of the duration of the second as the 86,400th part of the mean solar day was basically arbitrary and part of our tradition. In 1956, the International Committee for Weights and Measures, CIPM, defined the SI second as a specific fraction of the tropical year. Between 1955 and 1958, a joint experiment of the National Physical Laboratory and the U.S. Naval Observatory was conducted to measure the value of the Cesium-133 atom's hyperfine transition frequency. It is in this experiment that the value of 9,192,631,770 transitions per second was measured, which was adopted in 1967 by the CIPM as the new definition of the second, keeping the value as close as possible to the former one naturally. In 2019, a new international system of units known as SI was established in terms of a set of 7 defining constants. The complete system of units can be derived from the fixed values of these defining constants expressed in the units of the SI. These 7 defining constants are the most fundamental features of the definition of the entire system of units. The unit of time remained with some minor editorial changes, and it has a strategic position in primary metrology since all the base units of the new SI are related to the second except the mole. In a cesium atomic clock, the frequency of a microwave source is carefully adjusted until it hits the resonance frequency corresponding to the energy difference between the two ground state hyperfine levels of the cesium atoms, which is 9,192,631,770 Hz. The atoms absorb the microwave radiation, and a feedback signal generated from the absorption signal is used to keep the microwave source tuned to this highly specific frequency. The time display is generated by counting electronically the oscillations of the microwave source. The best time measurement standard in Mexico uses an arrangement known as an atomic fountain, in which laser-cooled atoms are launched upwards through a microwave cavity before falling back under gravity. Using cold atoms means that the interaction time can be far longer than in a thermal beam clock, also developed at Cesium, giving much higher spectral resolution. With careful evaluation of systematic frequency shifts arising from environmental perturbations, today's best cesium fountains have reached accuracies of 1 part in 10 to the 16th, though measurements must be averaged over several days to reach this level. They contribute as a primary standard to the International Atomic Time, TAI. In the case of the Mexican fountain clock, the hyperfine frequency measured is shifted 1.233 thousandths of hertz due to local systematic effects such as Earth's magnetic field, thermal radiation, and mechanical collisions between cesium atoms. This is an expected offset which can be corrected easily. The uncertainty or quality of the frequency measured is 29 millionths of hertz, which means that this clock needs more than 100 million years to accumulate a second early or late of error, becoming an ultra-high precision timing machine. We may not always realize it, but precision timing underpins many features of our daily lives. Mobile phones, financial transactions, the internet, electric power, and global navigation satellite systems all rely on time and frequency standards. Thanks to this capacity, Cesium can disseminate time signals to provide precision time measurement across all sectors of business and industry. We are the keepers of time for Mexico. But why is time important? Well, time is critical to certain services used within most organizations, yet many organizations are unaware of their dependence on time, the source of their time, or the existence of a world time standard. As systems grow in complexity, becoming global and mobile, access to resilient, accurate, and precise time is a necessity in both the private and public sectors worldwide. Without accurate and resilient time, critical functions and services can become unreliable, inaccurate, or unavailable. Now we are going to answer an important question related with which sectors and industries need timing and synchronization capabilities developed and disseminated by Cesium. We'll be frank, everyone needs it, but being realistic, some important sectors are highly dependent on time synchronization, and they are described in this figure. Telecommunications is maybe the most important one due to all services and functionalities that it gives to society nowadays. Our cell phones are important tools and will be indispensable in the near future. With the advent of new technologies, connectivity and transmission data rates will be important benchmarks to deploy 5G networks, for example. The internet is central to an endless number of services on which we rely every day. IoT represents the next step towards the digitalization of our society and economy, where objects are interconnected by creating communication networks through data exchange. Thanks to accuracy and availability of Cesium time signals, users will enjoy an even wider and stronger data network. Global Positioning System, or GPS, has become the de facto time standard for many commercial users because of its relatively low cost and ubiquitous availability. However, since 90s, experts have identified overdependence on GPS as a growing vulnerability within critical infrastructure. In 2017, 5.8 billion global navigation satellite system devices, or GNSS devices, such as those using GPS, were in use. By 2021, this number is forecasted to increase to almost 8 billion, an estimate of more than one device per person on the planet. As a result, critical infrastructure, even national security, is based on foreign systems controlled by defense departments of other countries like GPS or GLONASS, and those services cannot be certified. This represents a high risk for investors that have developed 4G networks in Mexico, for example. There are other technologies that are currently used for time stamping as atomic clocks and the Network Time Protocol, NTP. However, the first one can offer stability, but cannot be traced to a common time standard, and the second is only accurate over wide area networks to a few tens of milliseconds. Until recently, GNSS devices were viewed simply as radio receivers. However, they are actually computers with similar security risks. Threats include denial of service attacks or jamming and the introduction of bad data into the system, or spoofing. The advent of software-defined radios has increased the ease and lowered the cost with which these types of attacks can be launched. Efforts should be made to ensure accurate and resilient timing for GNSS devices. Moreover, the GNSS signals are weak and interfere, whether natural or induced, distorts time stamping. The signal levels are even below the natural background radiation level, or noise floor. Solar storms and reflections in urban environments are the most common natural ones. Thus, organizations have to evaluate the degree of dependence on accurate timekeeping to implement redundant architectures using time signals traceable to the official Mexican time, or UTC, CNM, and back up time systems based on GNSS or another time sources. In order to know your timing requirements, please address the following steps. 1. Identify what services or functionalities require time for operation within your organization. 2. Identify the primary source of time for your organization. 3. Determine the level of time performance, accuracy, and resilience needed for your systems or applications. 4. Is your organization's time traceable to the principal source of time? 5. Does your organization need global synchronization or local synchronization? Now, we are going to discuss a new mobile technology which is a key element of the Industry 4.0 and highly time-dependent. We are talking about the 5G networks. This new disruptive technology, compared with 4G LTE networks, is faster, more efficient in terms of energy and spectrum use, cheaper per bit, and allows hyperconnectivity. 5G enables a new kind of network that is designed to connect virtually everyone and everything together, including machines, objects, and devices. 5G wireless technology is meant to deliver higher multi-Gbps peak data speeds, ultra-low latency, more reliability, massive network capacity, increased availability, and a more uniform user experience to more users. Higher performance and improved efficiency empower new user experiences and connects new industries. 5G's full economic effect will likely be realized across the globe by 2035, supporting a wide range of industries and potentially enabling up to $13.2 trillion worth of goods and services, according to a recent study of Qualcomm Technologies. 5G networks are highly time-dependent in terms of stability, accuracy, synchronization, and redundancy. Could you imagine an autonomous car which suffer a delay uploading telemetry data related with traffic, for example? Or a loss of energy in the smart grid associated with time synchronization failures? Thinking about all these things, we understand the need for a high-performance, monitored, and always available time source. In Mexico, Cesium is the official timekeeper. Depending on the user's requirements, Cesium's time can be delivered using different techniques. Thinking about that, Cesium has developed a strategy that consists in implement official Mexican time replicas throughout the national territory and disseminate time signals more efficiently. This initiative is called the National Synchronization Network. Under this scheme, each replica uses a local oscillator with a time performance depend on time specifications in a transfer time system developed at Cesium. Compares the local oscillator with the official Mexican time, UTC, CNM, using GNSS as a comparison pivot, not as time sources. This comparison permits to create a replica of UTC CNM. Another solution is UTC CNM traceable time over managed fiber links using precise time protocol PTP that is constantly monitored and certified at the point of delivery. PTP can deliver synchronization over long distances using telecom fiber networks, employing dedicated channels or PTP compatible switches. The latency to each endpoint is continuously measured by the protocol and corrected. Actually, Cesium's NTP servers receives more than 300 million synchronization requests per day, attending different sectors, users, and applications. The Cesium's time and frequency capabilities are also used to calibrate references of secondary laboratories and attend requirements of other time-dependent magnitudes at Cesium. Thanks for watching, and remember that Cesium is working with industry and science to advance innovation and improve quality of life.